Hello, this is Junhyeok, and today I'm going to introduce our research on improved numerical differentiation by Lagrange interpolation. First of all, there are functions in nature that can't get a derivative, such as the middle of a mountain or the slope of a coastline. You can approximate several differential equations, such as the forward and the central differential, by substituting very small differences like values of h as differential coefficients. We use Taylor's theorem to calculate the performance of the forward and the central formulas, and find out that the central difference formulas are much more accurate, because the error of the central formula approaches zero is faster than the speed of the forward formula. In this study, we developed a faster difference formula than the existing difference formula. The key to the new differential formula is a Lagrange interpolation polynomial. The expression makes it simple to obtain polynomial functions of n order or less that pass all n plus 1 points. In addition, the following theorem is known for the error of the Lagrange interpolation polynomials and the actual polynomial. When Pn is an nth order Lagrange interpolation polynomial given at an equal interval of interpolation points, the error of f'x and p'x is n-1 multiplied by h times. At this time, if n is 4 or higher, the error decreases faster than the conversion difference equation with h squared or the central difference equation with h cubed. Therefore, we took the idea from Lagrange interpolation polynomial and made the study goal to obtain an improved difference formula. In previous studies, the differential of the Lagrange interpolation polynomial was obtained when the number of interpolation points was odd. The differential p'2k of the Lagrange interpolation polynomial with an interpolation point of 2k plus 1 is as follows. We aim to obtain a differential of the Lagrange interpolation polynomial when the number of interpolation points are even, and finally obtain an improved differential expression using the Lagrange interpolation polynomial for all natural numbers. If the interpolation points are odd, the expression is symmetrically offset by the center point. But if the interpolation points are even, the expression cannot be cleaned up as if it were odd because there are no center points. So we considered odd number of points, excluding the variant point of even numbers. So in the next process, we were able to obtain the differential expression using the idea of considering just one point. First, we found the interpolation polynomial p2k-1 that passes through all 2k points as shown in 1. And consider ni, which is expressed as an expression of x, is shown in 2. Differentiating ni gives n'(i) as shown in 4. When I is equal to k, how to organize expressions is a key idea to obtain differential expressions. When I is equal to k, n'(i) is equal to 5. And if you substitute t and 2k minus t for the values of u, you can obtain each of the following expressions. And when you add these two together, you can see that the expressions cancel each other out. Therefore, when I is equal to k, only the case when u is equal to 0 is considered. This expression is that. Using the when I does not equal to k, the expressions comes as 6, and from this expression and 5, n'(i) can be expressed as 7. If we substitute this for p'2k-1, we get an equation like 8, which is the difference equation we finally get. Using the error in the Lagrange interpolation polynomial, the process from 9 to 12 finally shows that the error of the differential equation is proportional to h squared 2k minus 1. Next is the validation of the findings. We applied the differential equations obtained earlier to find out the differential coefficients of the following 6 elementary functions. Python calculated the error between the differential coefficient and the appropriate value obtained by the differential equation, which is known as a representative example of the Lunge phenomenon. We were amazed at the results. We took the coordinates of the 6 interpolation points as shown in, and obtained the differential coefficient in the differential equation. As you can see, when the error is doubled from the side to the side, as if expected theoretically, the error is doubled. For the rest of the functions, the theory and the results were in good agreement. Finally, I will present the significance of the study. This study expanded the Lagrange differential formula, which is established at the existing odd interpolation points, to be used even when an even number of interpolation points were given. We also demonstrated that our Lagrange difference can be a much better choice than the existing difference by verifying that it performs well when applied to real-world situations. Thank you.